Have you ever stopped to think about electricity? It's amazing. It powers our lights, our computers, and even the phone you might be holding. But how does that electricity get from a big power plant, maybe hundreds of kilometers away, all the way to your house? It doesn't just travel in a straight line, it needs help. This is where a very special device comes in, a device called a transformer. Transformers are like the secret superheroes of our electrical world. They are working all the time, day and night, making sure we have the power we need, right where we need it. They are not the robots from the movies, but they are just as important for transforming our world. You might not see them very often, but they are everywhere. They are in big metal boxes on power poles in your neighborhood. They are inside many of the electronic gadgets you use every single day. Think about your phone charger. That little box you plug into the wall is actually a small transformer. Its job is to take the powerful electricity from the wall socket and change it into the gentle electricity your phone needs to charge its battery safely. Without these devices, our electrical system just wouldn't work. They are the crucial link that makes everything possible, connecting the big power sources to our small, everyday lives. So, what is a transformer really? In simple terms, it's a machine that changes the voltage of electricity. Voltage is like the pressure of water in a pipe. Sometimes you need very high pressure to push water over a long distance, and other times you need very low pressure so you don't break a delicate sprinkler. Electricity is the same. Transformers can take a high voltage and make it low, or they can take a low voltage and make it high. This ability to change the pressure of electricity is what makes them so incredibly useful and essential for our modern way of living. In this essay, we are going to take a journey inside the world of the transformer. We will look at its main parts and see how they work together in a very clever way. We will learn about something called electromagnetic induction, which sounds complicated but is actually a really cool science idea. We will also explore what it means to step up or step down the voltage. By the end, you'll see that these quiet, humming boxes are truly the unsung heroes that power our entire planet, making our electrical grid a marvel of science and engineering. Consider this: science rules. So why can't we just send the electricity straight from the power plant to our homes? Well, it all comes down to a big problem: energy loss. When electricity travels through a wire, some of its energy is lost as heat. You might have noticed that a wire can get warm when electricity flows through it. Now, imagine a wire that is hundreds of kilometers long. A lot of electricity would be wasted just heating up that wire. This would be very inefficient and very expensive. We want as much of the power as possible to reach our homes, not get lost along the way. The solution to this problem is to use very, very high voltage. Think of it like this. Imagine you need to move a lot of water through a very long, thin hose. If you use low pressure, the water will just trickle out the other end. But if you use very high pressure, you can force a lot of water through quickly. High voltage electricity is like that high pressure water. By sending electricity at extremely high voltages, sometimes hundreds of thousands of volts, we can push a lot of power over long distances with much less energy loss. This makes the whole system much more efficient. But here is the new problem. You can't use super high voltage electricity in your house. It would be incredibly dangerous. Your toaster, your television, and your lights are all designed to work with a much, much lower voltage, like 120 or 240 volts. If you tried to plug them into a high voltage power line, they would instantly burn out and could cause a fire. We need a way to have high voltage for the long journey and low voltage for our homes. We need to be able to change the voltage easily and safely. This is exactly why we need transformers. They are the magical changing stations for electricity. A transformer near the power plant steps up the voltage to a very high level for the long trip across the country. Then, as the electricity gets closer to your town and your house, other transformers step down the voltage in stages. They reduce it to a safer, usable level. So, transformers solve the puzzle by allowing us to use high voltage for efficient travel and low voltage for safe use in our daily lives. They give us the best of both worlds. To understand how a transformer works its magic, we first need to meet the team of parts that make it up. A basic transformer is actually quite simple and has three main components. The first two parts are coils of wire. A coil is just a wire that has been wrapped around and around like a spring or a spool of thread. The first coil is called the primary coil. This is the in door for the electricity. The electricity from the power source flows into the primary coil first. This is where the whole process of changing the voltage begins. The second part is another coil of wire called the secondary coil. This is the out door for the electricity. After the transformer has done its job, the new, changed voltage electricity flows out from the secondary coil to power our devices. The primary coil and the secondary coil are the two most important actors in our story. They are not physically connected to each other. You cannot trace a wire from one to the other. They are separate, which is a very important part of how the transformer works its magic. The energy has to jump from one to the other in a special way. The third main part is called the core. The core is a piece of material that both coils are wrapped around. In most transformers, the core is made of a special kind of iron. You can think of the core as the stage where the primary and secondary coils perform their act. Its job is to help guide the energy from the primary coil over to the secondary coil. Without the core, a lot of that energy would get lost and float away. The iron core concentrates the energy and makes sure as much of it as possible gets transferred, making the transformer very efficient. So there you have it. The primary coil, where electricity goes in, the secondary coil, where electricity comes out, and the iron core, which connects them without touching. These three parts work together in a beautiful dance of physics. The number of times the wire is wrapped in each coil is also super important, but we'll get to that later. For now, just remember this team of three. They are the fundamental building blocks of almost every transformer in the world, from the tiny one in your phone charger to the giant one at a power station. Let's look more closely at the heart of the transformer, the iron core. This part is so important because it acts like a bridge for energy. But it's not a normal bridge that you can walk on. It's a magnetic bridge. The core is usually made of a special type of iron called soft iron or silicon steel. This material is really good at becoming a magnet and then losing its magnetism very quickly. This ability is crucial for how a transformer operates, as the energy transfer relies on a constantly changing magnetic field. The core makes this process strong and efficient. Think of the iron core like a superhighway for magnetism. When the primary coil creates a magnetic field, the core's job is to contain it and guide it directly to the secondary coil. If the coils were just sitting in the air, the magnetic field would spread out in all directions, like the ripples from a stone dropped in a pond. A lot of that magnetic energy would miss the secondary coil completely. The iron core prevents this by being so good at carrying magnetism. It captures nearly all of the magnetic field and funnels it precisely where it needs to go. An interesting thing about the iron core is that it's not a solid block of iron. If you look closely at a large transformer's core, you'll see it is made of many very thin sheets of iron, like a deck of cards. These sheets are called laminations, and each one is coated with a thin layer of insulation, like a varnish, so they don't touch each other electrically. This is done to reduce energy loss inside the core itself. A changing magnetic field can create small, swirling electrical currents in the iron called eddy currents, which waste energy as heat. By using thin, insulated sheets, these currents are kept very small, making the transformer much more efficient. So the core is not just a dumb piece of metal, it is a carefully engineered component designed to do one job extremely well: guide a changing magnetic field from one coil to another with as little energy loss as possible. It is the silent, steady heart of the machine, ensuring that the magic trick of transforming voltage happens smoothly and efficiently. Without this special iron core, transformers would be far less powerful, and our electrical grid would be far less effective. It's a brilliant piece of applied science. Now that we know the parts, let's see how they work together, step by step. Everything starts at the primary coil. Remember, this is the in door. We connect a source of electricity to this coil, but there's a catch. A transformer only works with a specific kind of electricity called alternating current, or AC. This is the type of electricity that comes from our wall sockets. In AC, the electricity doesn't just flow in one direction. It rapidly flows back and forth, changing its direction many times every second. This constant change is the key to everything. When this alternating current flows through the wire of the primary coil, it does something amazing. An electrical current flowing through a wire always creates a magnetic field around it. You can try this with a battery, a nail, and some wire to make a simple electromagnet. Because our current is alternating, always changing direction and strength, it creates a magnetic field that is also always changing. The magnetic field grows stronger, then weaker, then flips its direction, then grows stronger again, over and over, in perfect sync with the alternating current. This pulsing, changing magnetic field is the first half of the transformer's magic trick. The primary coil's job is to take the incoming electrical energy and convert it into magnetic energy. Specifically, it creates a constantly changing magnetic field. It's like a translator, changing the language of electricity into the language of magnetism. The coil, which is just a simple wire, becomes a powerful, pulsating electromagnet as soon as the AC power is turned on. Its magnetic influence fills the area around it, and most importantly, it fills the iron core. The energy is no longer in the wire itself, but in the invisible magnetic field that the wire has created. This field now extends throughout the iron core. This is a critical moment in the process. The electricity has done its job in the primary coil, and now the magnetic field is ready to take over and carry the energy to the next step. The primary coil has successfully loaded the energy onto the magnetic bridge, the iron core, ready for it to be sent across to the other side, to the secondary coil. Here comes the coolest part of the process, a scientific principle called electromagnetic induction. This principle was discovered by a scientist named Michael Faraday, and it's the reason transformers work. The principle says this: if you have a changing magnetic field near a coil of wire, it will create or induce an electrical current in that wire. It's the reverse of what happened in the primary coil. There, electricity made a magnetic field. Here, a magnetic field is going to make electricity. It's a two-way street. The changing magnetic field that was created by the primary coil doesn't just sit there. It travels through the iron core, and on its journey, it passes through the secondary coil. Remember, the secondary coil is just sitting there, not connected to any power source. But as the pulsing, swelling, and shrinking magnetic field washes over its wires, something magical happens. The magnetic field pushes and pulls on the tiny electrons inside the wire of the secondary coil, forcing them to move. The movement of electrons is what we call an electric current, so the energy has jumped the gap. It went from being electrical energy in the primary coil to magnetic energy in the core, and now it's back to being electrical energy in the secondary coil. No wires connect the two coils, but the energy was transferred perfectly through the invisible force of magnetism. This is why transformers hum. The rapidly changing magnetic field actually causes the metal core to vibrate slightly, creating a low humming sound. It's the sound of energy being transferred. This process of induction is incredibly efficient. In a well-designed transformer, over 99% of the energy from the primary coil can be successfully transferred to the secondary coil. Very little energy is lost in the jump. This is why transformers are such a brilliant and practical invention. They allow us to change voltage levels without losing a lot of power in the process. It's all thanks to this beautiful invisible dance between electricity and magnetism, happening thousands of times every minute inside that metal box. The energy has successfully made the leap across the magnetic bridge and arrived at the secondary coil. An alternating current is now flowing in this second coil, induced by the changing magnetic field. This new current is ready to go out and do work, like lighting a lamp or charging a battery. The secondary coil is the outdoor of the transformer, delivering the newly transformed power to its destination. The journey from electricity to magnetism and back to electricity is complete. The transformer has done its primary job of transferring power from one circuit to another. But the transformer didn't just move the power, it changed it. The voltage of the electricity coming out of the secondary coil is different from the voltage that went into the primary coil. How is this possible? The secret lies in the number of turns or loops in each coil. The relationship between the voltages is directly related to the ratio of the number of turns in the two coils. It's a simple but very powerful rule. The magic isn't just that the energy jumps the gap, but that we can control what that energy looks like when it arrives. Let's think about it with a simple example. Imagine the primary coil has 100 turns of wire and the secondary coil has only 10 turns. The secondary coil has 10 times fewer turns than the primary. As a result, the voltage induced in the secondary coil will be 10 times lower than the voltage in the primary coil. If you put 120 volts into the primary coil, you will get only 12 volts out of the secondary coil. The number of wire loops acts like a gear ratio for voltage, allowing us to change it very precisely. This is the key to the whole device. By simply choosing how many times we wrap the wire for the primary coil and how many times we wrap it for the secondary coil, we can design a transformer to produce almost any voltage we want. We can make the voltage lower, or we can make it higher. This simple design choice is what gives the transformer its incredible versatility. The secondary coil doesn't just receive power, it delivers a custom-made voltage, perfectly tailored for the job it needs to do. Now we can understand the two main types of transformers, step-up and step-down. The names tell you exactly what they do. A step-down transformer is used when we need to decrease the voltage. As we saw in our example, this is done when the secondary coil has fewer turns of wire than the primary coil. This is the most common type of transformer you'll encounter in your daily life. The charger for your laptop or phone is a step-down transformer. It takes the high 120 or 240 volts from the wall and steps it down to the low voltage, like 5 or 20 volts, that your device's battery needs. Imagine a big fast-flowing river. A step-down transformer is like a dam that takes that powerful river and lets out a small, gentle stream. The power is still there, but the pressure or voltage is much lower and safer to handle. The large green or gray metal boxes you see in neighborhoods are step-down transformers. They take the medium-high voltage from the main power lines running along the street and step it down to the safe, usable voltage that is sent directly into your home. They are the final gatekeepers that make electricity safe for us. The opposite is a step-up transformer. You can probably guess how this one works. It is used when we need to increase the voltage. This happens when the secondary coil has more turns of wire than the primary coil. If the secondary coil has 10 times more turns than the primary, it will step up the voltage by 10 times. These transformers are found at power plants. A power plant might generate electricity at a few thousand volts, but to send it across the country efficiently, it needs to be at hundreds of thousands of volts. A giant step-up transformer does this job. Think of the river again. A step-up transformer is like a giant pump that takes water from a lake and forces it into a narrow pipe at extremely high pressure to send it over a mountain. Step-up transformers take the generated power and give it the massive push it needs to travel long distances with minimal loss. So, step-up transformers are used at the beginning of electricity's journey, and step-down transformers are used at the end. Together, they form a perfect system for moving electrical power efficiently and safely from where it's made to where it's used. As we have seen, the transformer is a simple but truly brilliant device. It has no moving parts, yet it performs one of the most important jobs in our modern world. By using the fundamental principles of electricity and magnetism, it allows us to change the voltage of AC power easily and incredibly efficiently. This ability to step voltage up and step it down is not just a neat trick. It is the foundation upon which our entire global electrical grid is built. Without transformers, we would be stuck in a world where electricity could only be used very close to where it was generated. From the moment electricity is created at a power plant, transformers are there. A huge step-up transformer boosts the voltage for its long cross-country journey. Along the way, at substations, large step-down transformers lower the voltage for distribution to towns and cities. Then, on a pole or pad right in your neighborhood, another step-down transformer lowers it again to make it safe for your home. And even then, the journey isn't over. Tiny transformers inside your electronics, from your computer to your television to your stereo system, are busy stepping the voltage down even further to power delicate microchips. Every time you flip a switch, you are relying on a whole chain of transformers working in perfect harmony. They are the silent, humming guardians of the electrical grid, working 24 hours a day, 7 days a week, to manage the flow of energy. They make it possible to power a huge city with a power plant hundreds of kilometers away. They make it possible to run a tiny, sensitive computer chip from the powerful current in your wall. They are a perfect example of how a simple and clever scientific idea can completely change the world. So, the next time you see a metal box on a utility pole or plug in your phone charger, take a moment to think about the amazing science happening inside. The elegant dance between the primary coil, the secondary coil, and the iron core is a testament to human ingenuity. Transformers are not just pieces of equipment, they are the enablers of our connected, illuminated, and technological society. They truly are the unsung heroes that power our world, and that is some seriously cool science.